you explain, if that's a good place to start, what is ray tracing?
Yeah. Ray tracing, I think, really simply put, is just an algorithm that approximates the behavior of light as it interacts with objects and materials in a scene. And a scene in this case is like if you think of like a film scene or a game level,
Right.
or even just a still render of a phone or a camera or an object in an advertisement. So essentially, all it does is it simulates the way light comes into a scene. If it hits like
Hmm.
a reflective object, like a mirror, for example, or a transparent object like a window, it's going to simulate how light interacts with that, and that gives us some really important visual cues like shadows, reflections, things that if they didn't exist in an image that you took, for example, you would have no idea where things are in the scene. The depth perception that you have is not there anymore. So being able to approximate the behavior of light is really important in making things look plausible. In the case that you have something that isn't realistic, like a Pixar movie, like
Uh-huh.
it looks like that, but you still have shadows, you still have reflections, like color still influences what you see. And on the opposite side, if you're, a company making a product and you want that car to look perfectly realistic, but it doesn't exist yet, you still want ray tracing so that the car looks exactly as it would look like in real life, but you haven't made the car yet, or you haven't made the part or product yet. So I think it's a really important algorithm. It's been around for a long time, by the way. This is like some stuff that was done in the 70s and 80s, and computing power, essentially, the capabilities of computers have held back the implementation of ray tracing in many markets.
Yeah. It, it's I have a comment and then a question. I was watching the latest Avatar movie. The first one, from a visual perspective, I didn't think could blow my mind. I was totally immersed, and honestly, I didn't think I would be. I thought it was going to be hype. I was completely sucked in. The second movie, the story was interesting, but when they got into the water, it was another level of like it just defies logic. And I know we're going to eventually tie this to digital infrastructure and other things, but just as we imagine the ability to portray that or anything that our mind can imagine, it's really unbelievable.
Yeah, it's really crazy to think that someone can go make a movie, and yes, it's expensive, it takes a long time, but it's possible to make a completely computer generated movie where the people are essentially aliens and water is like fully realistic. Like,
Right.
yeah, I had the same experience watching both movies actually. To your point, it's you watch the first one, you're like, there's no way this can get better. Like, this
Right.
is really good. This is
Right.
really good. The simple things like the skin materials in the first Avatar,
Right.
those kind of things make a big difference. The fact that there's some simulation there also helps with the body. But going into water is always a place that's really difficult to simulate, and it's even more difficult to make it look good when you sit while you're simulating it. And so this is something that James Cameron has been working on for decades now, and like these critical pieces of technology that enable something like Avatar to look as good as it looks. But like to tie it back to digital twins and like real applications there in
Right.
enterprise, it's the same type of problem that you have when you want to simulate, how does a wind turbine, interact with the ocean floor or
Oh.
and those kinds of things. And so it's really important to be able to do it both for consumer graphics and movies and games and television, but also to use the same techniques and algorithms for product design and engineering as well.
Did ray tracing replace something, or were there other technologies? I know you said it's been around, at least conceptually, for a while. Um, but and as it continues to evolve, it's like saying TVs have been around for a while, and we're at 8K and moving on into quantum dot computers and all this other, or TVs and all this other cool stuff. What are some of the other technologies that are coming along or have been there to fool us into thinking this thing that came out of an imagination is real?
Yeah, that's a great question. There is a different approach to solving this problem. It's called rasterization,
Mm,
and it's really what the GPUs are really, really good at. So when you get like really high frame rates when you play like Call of Duty on a modern GPU today,
hmm
all of that's rasterized. The great thing about rasterization, because it's been the focus of hardware GPU vendors for so long, is
hmm
that it's really fast. The downside is that it doesn't account for light. It's not simulating light. All it does is it takes a triangle and paints a color on it. You can do a lot more stuff with that. For example, a lot of our favorite game developers have figured out how to make that look like it's ray traced.
right.
And that's like these are workarounds because ray tracing is too computationally intensive. It requires like changes to the game itself to do ray tracing. Everyone's essentially figured out how to make rasterization look as close to ray tracing as possible. The problem with that, however, is we always forget that like to your point about motion graphics, when things are moving, you have to be able to paint thousands of frames. I mean, if you're playing a game at 60 frames per second, you have to be able to literally approximate shadows without knowing where real lights are or where the
Right.
shadows should be. Um, on a console that millions of people might have downloaded this game, got to play this game, right? So you
Right.
can imagine the complexity in approximating what like the behavior of light is without even having the algorithm in place. It's insane. It's really crazy. It's I would say it's a huge portion of the time, money, power, and effort that goes into making this kind of content. And it's much easier if you can just flip a switch and turn on like something like ray tracing, which is physics based. And if you have a reflecting material in your scene, well,
Yeah.
you have reflections already. It's good to
Yeah.
go. You don't have to like go find and paint them in, and you're relying on the artist's technical ability to paint something that looks good. And there are certainly artists that can do crazy things, and we know them very well, and it's amazing to see what they can do. But in the end, it's like why do you have to do all of that effort if you can just flip a switch and in theory things will look physically plausible right off the bat, no
R-
effort.
Right. It's almost like rasterization is you're describing to somebody who's a sketch artist and they're sketching, and tracing is I'm actually creating it. Like the thing's doing it. There's no sketch. This is what it looks like. And when I was a kid in high school, my dad for 20 something years was on the shuttle program down at Mission Control. And one
Mhm.
day, I think the statute of limitations, he's long since retired, has expired, so I can confess this. But we got to go in with him and go to the shuttle simulator. And they had
Mhm.
multiple simulators, this particular simulator. And I'm looking at the complexity in this would have been what, 81, something like that, 80, 81, which seems crazy. Like you probably were even born then or barely born, right? But at that time, this thing was so amazing. And they were using these tools. One simulator is just how you manipulate all of the devices within the cockpit. But the other one was everything, the robot arm to get stuff back in to the shuttle. And it was incredible how important. Keep in mind with whatever the technology was in 1980, like it wasn't even a, x86 yet. Like a Radio Shack. I don't know what it was. Right, my watch has more power than that thing, but they had to simulate the shadows because with those bays open, as you got gear back into or whatever the mission was, if you were off, and we saw tragically sometimes if you miss by millimeters,
Mhm.
you miss everything. You tear the skin of the shuttle, you break some mechanism, and now the bay door stuck over. So they had to practice a million times before they ever went to space. And the shadows can because you have all these celestial bodies, you've got this gear moving. And so it's not just entertainment, like in that way. I'm sure there's a million more we could talk about. I've got to be able to simulate what this looks like so that when I do it in real time, I not only know what it looks like when it's done right, I know when it looks like when it's done wrong, right? And that's how like, I got to have my senses. I'm not gonna be out there to smell and taste, so I've got to do this visually. It just seems incredible I mean, are we talking about the same thing? Is this the same idea?
Yeah, this is definitely the future of like all manufacturing. I think space is a great example of the constraints placed on building something for space is insane. Like, you don't want to send someone up there to try to troubleshoot a problem, right? You want to
Right.
like look at all of the millions of possible scenarios, like you're in Doctor Strange, and at the end of it, you know which one's the perfect one, and you're
Right.
good to go, right? Like you want that, and you want
Right.
that for every product. Like if you wanted to go build a new space company or a new car company, right? Like
Right.
you don't want to go build a manufacturing facility in the beginning and then start rolling cars through that pipeline. What you want to do really is to design every part on a computer, essentially simulate every part on the computer independently as part of the car in the environment, all of those levels. And then once you're satisfied with the result, you go and you pull the trigger and you're good to go. You can go to production with that, and you know exactly how it's going to perform. So I think space is a great that's probably one of the earliest examples, publicly available examples. There's a lot of
Right.
defense as well, but
Right.
space is a great one because it's just not feasible. It's not economically feasible to build 25 prototypes and see how they fail. You really
Right.
just want to know once, sign it up once, and it's like a perfect mission. You're good to go. So it's really about like reducing the risk on a really large, complex project, and it gets better as the project gets more complex and more unfeasible in its current state, I think.
Yeah. Um, this reminds me of I think his name was Jeff. I apologize. I cannot remember his name now, but he was one of the guys in the robotics program at Saab. And
Mhm.
I believe this to be true. I fact checked it once before, and the interwebs is always accurate. But basically, he said we have mapped the surface of the moon much better than we have mapped our oceans.
Yeah.
And so, if you imagine for as complex, I mean, space for humans brings a level of complexity because it's trying to kill you the entire time, right? It's a very hostile environment.
Hmm.
Equal to or greater than is ocean at depth around before you ever get into seismic areas or magnetic anomaly areas or whatever. And when you're one of the things he was commenting was, look, in the celestial space, when you're in that vacuum, actually from a light perspective, it's almost black and white. It's not black and white, but it's much less complex to evaluate and do things there than in the ocean that has all of the filtering that's going on, all of the particulates that are moving through that you really don't have in a vacuum. Generally, I'm speaking generalizations. All of the complexity of the environment, marine life, all of these other things. And then, oh, by the way, pressure that is trying to rip this entire thing apart. And I got to imagine some of these tools that we're talking about to be able to help us to explore oceans. If I'm deploying, for example, I'm in the data center business. Microsoft has deployed data centers in the ocean to use tidal wave to help power them and to cool them. Like we're constantly seeking out where we can get more resources and how do we in this case use the ocean. It seems like we're going to need technology like this to go in there and simulate an environment that is as difficult as different kinds of complexity, but it's as difficult.
Yeah, I think like simulating like how a containerized like building or data center would operate like underwater I think it's a great example because the reason why Microsoft or a company like that would want to do that is that's more cost effective, right? But
Right,
on one end, on the far end of maybe like the Stone Ages, if you were to just take a container, throw it in like off the coast and see how it behaves, right? Does this
right,
work? No. Okay, let's move it like 4 inches this way, right? Let's keep
right,
playing around with this, turn those knobs in real life. It's quickly become way too expensive. So why would we do this in the first place? So
right,
if there's the ability to simulate how if I go place that thing underwater somewhere, let's pick this specific location on the planet, let's put it there virtually, see how it behaves. If that's really cost effective, it enables more opportunities for optimizations. Essentially, your product gets better, it's easier to make it, and also you have a better idea of how it behaves. So you're absolutely right. Like this is really critically important, and it'll become more important um, as more people want to do this type of simulation work. If it's unoptimized, you can imagine that a large portion of power consumed overall in the world, and also a large portion of power consumed in data centers, is going to be used for this purpose. And so it's really important to be ahead of that trend and to have a solution available that can really address that problem. Because if you can imagine this problem right now is like we can't buy GPUs, and a lot of the customers that we have they have data centers that can only fill a quarter of them because they run out of power too quickly. And you can imagine
Right.
if you double the amount of simulations you do on that hardware, well, you got to buy twice the amount of hardware, and how's that going to happen? So I think it's really interesting. I know I answered like two to your questions, but
Look, you're actually, we are for sure landing on hardware. But before we do that, so we've talked about, like I am not as big a gaming nerd as I used to be. I'm not saying I had a human rogue on a PvP server in World of Warcraft or a number of other things I might confess to in a different life. But um, in all seriousness, so when I would think of ray tracing or GPU in the past, I would think of making a movie. I would think of playing a game. You started to talk about modern manufacturing, and I remember I heard you speak once, and it was just this fascinating idea. So I want to tease this out a little bit, which is it was in the area of I think an artist painting something, for example, and as that artist is doing this creation, they have an idea in their mind. I'm thinking of just a classic artist, the Sistine Chapel or something. I have an idea in my mind, and I'm trying to express it across this canvas. And for most people, it takes decades to learn apply this paint in this way, wet. The final result in some amount of time in the future, dry. I got an approximation, but regularly they have to come back. I mean, that's why they're masters, and it's, whatever. But this barrier to entry, because you really have to master that skill. You were saying that, look, there's technology that exists and that's evolving that allows you accurately, as you create these things in a digital format, you can see what the final note is going to sound like, or paintbrush is going to look like, all the way down, depending upon the infrastructure that you have, to literally the fiber strokes, if you want to get that detailed. Can you talk a little bit about that idea and then how you think it might apply to, we start with manufacturing, but just the number of possibilities you talk about?
yeah, I think computer graphics is really interesting because you're using a computer to create something that's going to be viewed on another computer at some point, whether it's like a TV or an iPhone or something.
Right.
Um, it's really interesting just think about uh, if if you start with a blank canvas on a computer and you start to add stuff to it, it starts out pretty easy. You can start adding, objects.
Right.
You can start painting those objects. You can still see things. But when you go to a level of complexity where you have like a movie scene, you're in some train station, I think is a good example. There's a famous Pixar movie in a train station
Mm-hmm.
that caused a lot of issues on their infrastructure. When you go to that level, like it's really difficult from a feedback loop perspective to have to wait minutes, hours, days, weeks, or months. And in many cases, you can wait hours to see like what you're doing.
Right.
Let's say you have a sphere, there's a very simple, like unmodified sphere, you apply material to it. It might take you a few seconds to see what that would look like.
Right.
And that's really, you don't want to wait that long to see what it looks like, because if you apply that to maybe hundreds of objects in your scene, you're going to be waiting a long time.
Right.
Like we do this, that when I first started this in 2014, we played around with these tools on the nicest computers in the
Right.
market. Like we bought the nicest, the fastest, we install the tools, we optimize the tools, and we start to use it. And like even a simple simulation of taking a piece of cloth and it hitting a box, that took 8 hours to simulate about 20 frames of that on a $25,000 computer. And so it's like you can imagine, like if you have a lot of the stuff where you have a person that you're wanting to animate, right?
Right.
And his shirt's going to move around as he's moving around. You're already into the weeks to months to wait for that to come
Right.
back. And that's on one computer. It gets better if you have a data center
Right.
or farm, or you can use the cloud,
Right.
but your cost doesn't scale at all. It's just the other way. You can do it quicker, but then you're spending $1 million to get that result. And so the way we think about it is like in computer graphics, it's the feedback loop that really matters. And an even better example for maybe some of our listeners is like if you write code,
Mm-hmm.
imagine you write like some really great code, and you go to compile it and you wait like 2 months. And 2 months later, your code comes back and you forgot like one letter, just one thing you
Right.
forgot, a little thing, but you wouldn't have known because it took 2 months to compile. Like if you make a mistake in computer graphics, you're going to find out at the end when that render comes back.
Right.
Maybe you don't have the ability to go re-render that frame. Maybe you just have to like paint over it literally just to make it look good. And so this is the problem. I like to look at it from the content creation
Mm.
perspective because these are the artists that have these amazing visions, and the value that they provide is always going to be limited by like the computer on the other end that can take their vision and make it reality. And so the value of those artists is just limited by that. So why don't we just unlock their
Yeah.
potential creativity? On the manufacturing side, it's the same thing. Like
Yeah.
if it takes me as a startup 17 years to go design a car, that's a made up number. If it takes me a long time to go design a
Right.
car, as a startup, like I have to raise a lot of money. I have to convince a lot of people that they should wait a long time. And then also, even more importantly, the market might have changed so much that my car design is not no longer good. It's no longer, it's maybe not a hot market anymore. Maybe everyone's moved to buying trucks instead of sedans, and you design a sedan
Right.
for the European market, but you're in America, right? So I think there are like
Right.
there's lots of risks when the barrier to entry is so high. But if you can hire 5 guys and you can build a complete digital twins model, you can validate that model in a real world virtual environment that looks perfect, it behaves exactly as it would behave. And you can pick up the phone and say, hey, we're going to raise some more money. We're going to go make this car. This is the perfect design. We know it's going to work exactly as it's going to work. You can go forward from there. There's a lot less risk in that proposition. And so it's the same kind of like, you don't want to really wait. The feedback loop shouldn't be very long ever for anything that we do at this point, as
Right.
especially exiting like the industrial revolution. I think it's like, whether you want to make a car, a mug, I'm looking around my office, or like anything that you make, or literally you just want to be able to see what it looks like and make decisions based off that feedback. But if it takes forever, it's not worth it.
Can I give you an example that I heard the other day? I don't know how much this is. I know some of it is true now. The potential is blowing my mind, and the car reminds me of it. But this person was talking about shoes, in particular sports shoes. And so they were talking about, and I was totally with them when they were talking about, look, creating the design, the colors, the look, all the things that we might expect, right? Where before with a
Mhm.
car, like you'd shape it in clay and you do other stuff. So they talked about how they built the shoe, and I was like, okay, that's really cool. And then they started talking about, here's how I can simulate the different materials the shoe's
Yeah.
made out of. Oh, that's really interesting. And now here's the next level. So level 3. Now I can, without having to put it on a machine that flexes it 1,000 times, I can create, I can get 98% of that work done. I might do a sample to validate it, but I can get that flex and that torquing and apply the laws of physics in a certain way to see how long is that going to wear out. What happens if the human, or if you're like one of my kids who puts little slippers on her animal, and I'm not going to rat Jessica out because I think that would be inappropriate as a parent. But but if you're pigeon toed, if you're whatever, if your feet work a certain way, you can simulate how the shoe wears out, right? And so I'm listening to this, I'm like, wow, it's blowing my mind. They said, now let's take it to the next level. Say you're an elite athlete. If I can simulate the environment, the clay that shoe's running on, the concrete of the launch pad, my personal new favorite sport for people my age and weight, disc golf. I literally did a accidental flip off a disc golf pad not long ago. Terrified everybody. I wasn't hurt. But anyway, they just talked about, look, some of this exists today. And while we're talking about shoes, we're talking about cars, their point was, I can now create the environment that the car lives in. I can create the weather conditions. I can create it, not just its look and not just its wind tunnel measurements, which is all baseline and important. Many times we stop there because I got to get it to market, and it takes a while to generate all that. But what if I could take that car and or whatever we're talking about, and put it into a real world environment that simulates these things? There was just so many applications, and my jaw just kept dropping. And they said, what the barrier is the cost. It's you. I would have thought it's the software, and there is certainly the algorithms that you talked about for sure. I'm not trying to. So I don't want a bunch of rage email from the people who write these code that this, that it's not important. That's not what I mean. But you can come up with the most amazing idea. I'm Michelangelo, and I've got the most amazing idea either for a, a statue I want to carve or a painting I want to do, but my chisel is the size of a number two pencil, and I've got to, do this instead of having a wide array of tools or palettes, or my paintbrush is three threads, and I've got to, every day I got to go make new paint or et cetera. And so they said this palette that we see, we're getting to learn how to obviously create the visual and all this other stuff in whatever manufacturing that we're done, but I'm able to introduce it into an environment. For example, I can simulate the shelf life of a can of food. Will it actually last under these weather conditions or whatever? On and on and on. And it just blew my mind of possibilities. Now, I know some of that is hope to have, or not if, but when. Am I understanding this correctly? Is this the right way to think about the potential of not just ray tracing, but the infrastructure that enables that?
Yes. There are, I think if we picked every company that made a product today, that I think there'd be a great use case for every company, every enterprise to use the sort of simulation flow to make the product better.
Right.
I agree with you. Like it's definitely reducing cost. What we need to do is make sure that these engineers, these artists have the right tools. Essentially, like to
Right.
your point of like, if Michelangelo has like the worst chisel in the world, it's not going to be
Right.
worth it.
Right.
Or if it's your point, if it's a number two pencil, he's not going to make very much progress. Like we'll
Right.
see nothing out of him.
Right.
And so it's really important to arm those artists and engineers with the right things. But I think there's also going to be some added pressure in the future to ask from governments and watchdog organizations, like, what are you spending your money on? What are you spending your time on?
Mm.
Because if if you make a plastic product and it finds its way into the ocean, what happens to that product? Has anyone ever simulated? It's not just plastic; it's any part that has some waste associated with it. We should be simulating how that plastic part, interacts with the environment as it sits on the side of the road for hundreds, thousands, millions of years.
Yeah.
And I think that we're not there yet. And this is something that's going to happen in the future, I think, for sure, when we start getting questions like, Darwesh, when you go make this product, what happens when I die? When the product is, not useful
Right.
anymore, it passes its life. And to your point about food, even like there's so much efficiency that you can gain from making just anything if you just have a lot of data about how it behaves in the real world. And I think when we talked about this previously, you made this great point about it's reducing risk, but it's also reducing like the risk vectors for I don't want this product to go wrong or to behave in an adverse way in a certain environment. Like what happens if rain? Like I think there's some basic examples. Like if you make like a teak chair, right? You're
Right.
gonna, okay, let's see how it behaves with water, right? That's an obvious one, right? But like
Right.
what happens in other scenarios where maybe someone's gonna throw it away into a dump and like is it gonna biodegrade really efficiently or is it gonna take forever?
Right.
So I think um as time goes on and as more companies make more products more quickly, a lot of the stuff is going to need to be simulated for, and not just for, the shoe was going to perform even better on your foot because it knows, right, what you're trying to do with the shoe because
Right.
the company simulated it. But it's on the other side as well. It's like, how's it going to impact the world is also going to matter a lot. And then also like, do you consume all of the power in the world to try to simulate the perfect part? Can we reduce that a little bit so that the value add that this product provides the world is a net positive over a long period of time?
What is, I don't want to presume anybody knows what a GPU is, or if they think they know what it is, can you explain what it is and how it's different than a traditional computer part and its role in this explosion of technology that we're talking about?
Yeah. I'll try to do it without going into the architectural kind of details,
Okay.
which I think are like probably too low level and don't really matter. I would say that so GPUs are really good at massive parallel work. I think if you're curious, like, okay, why would I use the GPU?
Right.
Anything that you need massive parallelism for, GPU is great for. So
Okay.
if you look at the screen that you guys are watching this on or staring at right now, there are
Right.
millions of pixels on the screen, right? So a GPU is a great computing platform to draw pixels on a screen because there are millions of pixels. And the compute work that the GPU does is very similar for each pixel. It's just really, really massively parallel. So you want to draw as many pixels as you can as quickly as possible. That's where GPUs started. That's what they're really good at. There are a lot of compute workloads in the world that GPUs are really good at because these workloads are parallel, like
Hmm.
high performance computing, the simulation work that we talked about, and also, of course, AI workloads, which require
Hmm.
massive parallelism. A lot of data parallelism is required there. So GPUs are really good at that. Traditional computers, like the CPU that your computer is centered around, is not as parallel. It's very good at work that is less predictable, more like branchy work where there's a lot of ifs, if else's, those kinds of things.
Hmm.
And it's a really good flexible platform. Like CPUs, you can write a lot of code on. You can do whatever you want with. You're just not going to get maximum speed if you need that level of parallelism, that level of scale. That's what the GPU is really good at. So I think hopefully that's a I think good
Yeah.
high level.
Yeah. How long for what when you think of a GPU,
Mhm.
the modern version of it, how long has that been around? Like the emphasis of it. And then my second part, I guess, to the question is, when did we stumble on? I got a few years ago to go to NVIDIA as part of another project, and I got to meet their CEO Jensen, who's larger than life. He is a character. I really enjoyed meeting him. But when I listen to him, I love innovators that do this. Somehow they were the ones who thought of all the multiple purposes of I saw the GPU coming in this way. And I'm not saying he didn't, but it seems like whenever I bump into a visionary CEO or whatever, there's a lot less accident that in their mind it's way more purposeful. But so when did modern GPUs come around, and then when did somebody, do you think, in the way we're thinking about it now, say, holy smokes, this isn't just great at killing orcs or making the abominable snowman look fantastic in Monsters Inc. It can do all of these other things.
Yeah, so the original few generations of GPUs in like in the late 90s, they were fixed function, which just means that they hadn't gotten to the level of being able to program GPUs for non like drawing pixels on a screen kind of work.
Uh-huh.
That generation came very close, like both ATI at the time and NVIDIA pushed out products that had programmable cores essentially, which gave us the flexibility to do, in theory, whatever we wanted with it. There were huge limitations with the design at the time,
Right.
gotten much better over time. I would say that like the early 2000s, that was a big turning point in when companies realized that the more cores that you throw at the problem, like the faster that problem gets solved. And in some cases, you can extract huge efficiencies if you know what that design looks like. If you know, okay, I have a 2000 core GPU I want to use. Okay, how do I distribute my work over 2000 cores? That became a really big thing. What we've seen over time, though, is that GPU companies, they just keep adding more cores to the problem. Like the
Mm.
GPUs just they go from 2000, 4000, 6000, 18,000 now, and we're talking even bigger than that in the future. The downside with adding more cores is that it's really difficult for humans to write code that scales really well across tens of thousands of cores. So like the design of the GPU has stayed relatively the same over the past 20, 25 years. That certainly holds true. Um, the workloads have gotten much bigger because I think people just have realized that, oh, I can like even with simulation, I think is a great example. Like, back in the day, it was like, okay, can I simulate like this 1 meter cube only? And
Mm.
now it's like, can I simulate the entire Earth? Like we're talking
Right.
about simulating like plastics over millions of years now. And so like the
Right.
complexity of the problem has increased significantly. But the problem is a lot of these other solutions, all they do is throw more cores at the problem, more cores to the problem. And at some point, it becomes necessary to like rethink the entire architecture of the system and say, well, what if we just want to solve a modern simulation problem? What does this system look like throwing away all of the technical debt, all of the old architecture decisions that were driven by technical limitations, design limitations, thought processes, just things like that.
Right.
Um, that's what we're doing. We said, okay, look, what if all 25,000 companies that are going to build complex parts, um, what if they all just bought a chip and the chip solved that problem specifically for them?
Right.
And they didn't have to do anything special, and it didn't cost a lot of money, and it didn't consume a lot of power at scale. But it was sized for their modern workload, so they didn't have to say, "Oh, I got to go build a data center now to solve like the specific problem." And to your point, I have to go find some software vendor that may or may not do the best thing with it. There's some limitations there. There's some communication issues, across the stack. Why don't we just solve this entire problem all at once and then deliver just like a package solution that is optimized for this simulation?
When you talk about core sizes, is this does the card itself materially change its size? So, for example, I remember my original 286 computer with its turbo button. I thought that sucker was so fast it left skid marks on my desktop. It was, and the dot matrix printer that came with it. If I turned that thing on now, we'd go through the active shooter protocol. People would just think like there's something going on in the building. And of course, 25, 30 years later, we have the CPU, not the GPU, but the CPU in that thing is exponentially more powerful. But the machine, the physical dimensions aren't that much bigger. When you talk about the cores on the card, are we just shrinking like a CPU? Is it approximately a similar size? And sort of related to that, is it drawing the same amount of power? In other words, yes, we do more cores, but they're much more efficient than doing that? Or are they just getting exponentially bigger and now we're distributing them across large footprint?
Yeah, so there are some design vectors when you're designing silicon. So the first thing is transistors have gotten a lot smaller over time.
Right.
That's great. Thank you, TSMC, Samsung, Global Foundries, Intel. The transistor has gotten a lot smaller over the past 30 years, not past 50 years. That's really great. What that means is if you think of just one design vector, is I can stuff more cores, more stuff into the same area of silicon.
Mm,
That's really great. What also happened as transistors got smaller is they consume less power.
mhm.
So if I have a GPU from the early 2000s, for example, that might have 900 cores, one today might have 18,000 cores and it would consume
Right.
so much power and be similarly sized.
Okay.
That's great. That's super nice. There are some downsides, like power density is really high now,
Right.
like per area of silicon. That leads to huge problems. But also, like we're reaching the end of traditional transistor scaling, which means that if a GPU company wants to make a GPU that's twice as fast, they have to figure out a way to not rely on the transistor itself, the basic building block of that chip, to give them the ability to put so many more cores in and still consume the same amount of power. There is a we internally, like, we measure this, and there is a plateau that we've seen over the past 3-4 years in this efficiency metric, where essentially it's like I can throw more cores to the problem in one like specific area in one chip, but the power just starts to increase like significantly, and the performance doesn't increase as much as we would hope. So
Right.
um, it's gotten much better. What I will say is, if you look at a modern GPU board, I'm looking around. I used to have them all around here. A modern GPU board, they've gotten smaller, actually, what's really interesting versus the older ones.
Right.
But the problem is that they consume so much power that cooling is a much bigger issue. So that's where a lot of the time goes now, is like, how do we cool this thing really efficiently? How do we, at really high wattages and like higher voltages than we were used to initially, like how do we make that more efficient? And so there are companies now that just specialize in cooling, essentially, just to make
Mm,
sure that these 1,000-watt chips, you can deploy them and they won't blow up your house, or they
right.
won't blow up your rack or whatever.
So as we've talked about the role of the infrastructure, the benefit of all of these tools we've talked about, hopefully to help human beings flourish, and they're going to be applied in all these different ways, not just manufacturing, although that's the one we kind of focused on today. There is a cost to buy traditional infrastructure today. There's power things. Can you talk about what does the world mean by silicon IP, and what role does it play to help serve this customer base, but maybe mitigate some of the constraints of the GPU infrastructure as we know it today.
Yeah. Um, Silicon IP, we're a Silicon IP company. What that means is we spend all of our time designing what the chip will look like, how
What
it'll
does
how
IP stand for, if you don't mind me?
just intellectual property.
Okay.
Yeah, it's interesting. It's used. It's the same like legal term as IP. It doesn't. It's not a different word, but it means something completely different. In our case, it's like the actual code. It is intellectual property as well, like patents
Right.
and proprietary, algorithms and things that we invent. But in the end, it's just like a code base that we can deliver to a customer. When we talk about Silicon IP, all we focus on is designing the chip. What that means is we work with the customer and the customer says, Darwesh, I want to go make a data center chip. They don't want to go, or they don't have the expertise to go design the IP that we develop, like the
Hmm.
graphics IP, the ray tracing IP, the simulation IP. We're really good at that side. So we kind of partner with our customers. They license our IP, they go make the chip out of it, and they go sell
Hmm.
that chip. We take a royalty at the end of it. So there are some other companies that do this. There are actually a lot of IP companies in the world today. Like I'll give you a great example. If you look at your phone, there
Hmm.
is a application processor in the middle of your phone. It could be made by Qualcomm, Apple, Samsung, MediaTek, or any of those mobile companies. Not all of the stuff that goes in that chip is made by that company. They license IP from companies like us that specialize in those parts. So there are companies that specialize in like networking, companies specialize in CPUs, for example, GPUs, network, neural processing units, video encoders. There's lots of parts in the ecosystem. And so what we would do
Hmm.
is we just work with those companies that go license it to go make the chip. What that means for us is that we don't spend as much money speculatively making chips. We design
Hmm.
the IP. We have a customer at the end of it that wants to license it, that will go spend the money, tape out the chip, and we can work with them really closely on that. So it's a really interesting, like it's almost a hidden business in the entire tool chain of like IP all the way down into a server that you can buy, put into a data center. We have really good visibility into the entire end to end. That's why I think we're on this, where we're having this conversation is
Yeah.
you're at the very end of that, right? Or very
Right.
close to the end of that, where you might not care who develops the IP, but it does matter. Like our guidance in helping customers at every level down the supply chain, in understanding how they should architect the server, where they should put the servers in the data center, and all those things really do matter. And our goal is to make sure we extract as much efficiency as possible out of the design that we make, as well as the tool chain and going into the servers, into the phones, into the consoles, and all those kinds of things.
Yeah. Besides the obvious for me benefit of because your customers are my customers, right? They get this intellectual, they license this from you, this intellectual property, they apply it in their process and the things that they're making, and they're deployed in facilities like mine to perform all of these things and many that we haven't talked about. And so we want those things to be one, we want to serve our customer, but we want them to be as wildly efficient as possible. One of the things that caught my imagination about this, the role you guys play is the potential for agility. I don't care what organization you are, the larger you get, the more you have to harness the creative chaos. And I don't mean that as a criticism; it's just a fact. And and so you get more bureaucracy, you get more overhead, you get there's benefit to that, but usually it increases cost. It's not just the efficiency of the design. I'm not trying to pick on any of the GPU designers that we might think of, the big names that we might think of, but it is you can't help it. There's committees involved. There's all these other things. I'm not saying that in the world that you live in that doesn't exist, but it's almost like this new modern world of I have this. I have this almost like a Delta Force team. I love my military analogies, but like I've got this team, this elite team that can build these tools. We're more agile. We can test them quicker. We can get to failure faster, so we can get to success faster. Um, and it just leads to, in my experience, uh, more agile response to the marketplace. Am I overstating that? Do you think that's the right idea to think about this? Is there more that we should be thinking about?
I think yes, you're definitely right. We did a couple of additional things, I think differently, and a lot of people looked at us and were like, "Darwesh, you're absolutely well." There are a lot of people said we were insane by trying this in the first place, and then I said, "Well, we're also going to try to not hire people that are in this industry in the first place."
Mm,
Um, and that sounds insane. Like Darwesh, you're going to make a chip, you're going to hire people that don't make GPUs today, right, from your
right,
competitors, and the reason for that is we thought that it'd be good to take like a really completely fresh approach to the problem. And what that means is like, yes, we do the computer, like we install the tool and we see what it's like from the end user perspective. And we
right,
say, okay, like what's really happening here and how can we make this better? And hiring people that are not from the industry are great because they ask the dumbest questions, which is what I do all the time. It's like,
right,
okay, why is it like this? Oh, okay. And inevitably you find answers like, oh yeah, in the 90s it was this limitation, and so this has been like grandfathered in for the past 15 generations of
right,
products or whatever. And if you hire people that have been doing that for so long, I mean, we interviewed these guys and their feedback was, we'll just do the same thing for you. And I'm like, no, no, we want something really different, right? And to your point, you're absolutely right. It's half of its agility and being able to try out lots of different little things and see like what the most impact is. Once you pick a problem to solve, it's really great to say, okay, here's the full end to end. Here's what the user experience is. Here are the really painful parts. Oh, great. We can accelerate like all of these in a new chip design, solve that completely for the user. And they don't have to like worry about these crazy limitations that have existed for so long. So it's agility in that perspective, as well as like, let's hire people that intentionally can ask special questions. I'll put special questions that other people wouldn't ask. And some of them are just, it's a waste of time sometimes. Like
right,
it's a basics. Okay, Darwesh, it's for a good reason. Let me tell you the reason.
right.
But the things that are not good reasons anymore, at least, that's where we get the huge, advantage, the value, and lots of large companies, to your point, that opinion, that voice would never be heard. It's just not
Right.
possible
Right.
because you're selling 40 million of this part, the specific design a year. Why would you change that? There's no point in changing that.
Right.
So that's kind of value that we can provide to the market is essentially that we take a new approach. To your point, we're very agile. I mean, we spent 3 years, 3.5 years doing development on our part on our chip design, and it's available in the market today. It'll be in silicon at the end of the year. But that's crazy. 3 years to go from like basically no code written to a fully developed product that is faster and more efficient than the market leader today
Right.
is I think a testament to how silicon startups can be really agile,
Right.
which is something that I don't think you typically hear like a chip company being agile, but I think it's great that we can do it.
You're making a tool that's at the heart of solving this big problem for itself. Like that's, while I build data
Yeah.
centers, I need data, I need materials to build the walls better or whatever, but I'm not a material wall builder. I'm just a consumer of it. You're a designer and a consumer of it.
Yeah, I think it's really fun that we can sort of dog feed ourselves with our technology, even with rendering. Like we want to play around and see how much faster and how much better we can make this flow. And like I think it's really funny to think about it from a human perspective. Like I'm not the best artist and I don't have a really good patience, but it's really good to like expose my flaws in that as a person, but also just to learn what people are used to in that space becomes really important as well. And you're absolutely right. It's like it's really nice to be able to dog feed our own technology to ourselves, but it's also important because the simulation work the simulation tools that we develop, I'll give you a great example, like in the optics space that you mentioned with fiber, for example. Um, you know, if you can use both technology to better simulate, a laser that's going to drive a fiber optic link or a lens or an optic assembly, for example,
Mm,
or a full pluggable module, that'll also help the implementation of our customer silicon in the data center, which uses more efficient optics as a
mm,
result of this. And so you can create a really, really nice virtuous feedback loop if you try to address, or what we're doing, trying to address the core foundational aspect of making things, but making them better, make them cheaper, make them
right.
faster. So yeah, I agree with you. I think it's really exciting. I think it's really complementary to AI in the sense that, to your point, if you want to ask it a question, it's also good to have AI asking the simulation lots of questions as well. It can come up with lots of better questions than we can come up with. We see AI being really useful in those spaces where it'll be really good at controlling the flow and the outcome of simulations.
Right.
But the simulation is still done in a real physics environment where you can like look back and see, okay, why did it make this decision? Why did that particle hit that thing? Like it's not a black box necessarily. So it's really good complementary. I'm really excited to see and to show demos of how this can work together to provide some really, really good outcomes for every enterprise on the planet.
I gotta know, were you sitting around one day skating there in the Bay Area and, uh, having a great time? You said, man, I want to go do this. How did you get involved in doing something like this?
Yeah, that's a great question. I was one of those guys, I like to play a lot of games and GPUs were expensive. This was in 2013,
Right.
2014. My background is in the data center space, so I was not quite at your level, perhaps. I'll put it that way. I was putting servers in racks, putting racks in data centers, figuring out where they went. I have through work, I met a lot of people that were building render farms for film studios, and
Hmm.
over dinner, when people complain about like
Yeah.
work or things like that, and it's just really interesting to hear it. Oh, I got we built a 50,000 core render farm, and it still takes us a year to render a film. Like, really, a year? How is that going to work if you're making a movie and you have a budget, you have a deadline you need to hit
Right.
before it can go to theaters, right? And it's
Right.
like rendering is not the final stage of the process. It's not. It's like in the middle of the process. There's a lot
Right.
of post needs to happen, and so it became really interesting just for me to understand like why is this so bad? Like I thought we're in the future of like future technology age, right? Like
Right.
space age. Why are we spending a year waiting for a render to come back? And the more I dug into it, the more it became clear that this was like something that the demands had grown from a user. Like I want every movie I want to watch now is like Avatar 2. I think Dave, I think we can agree on that, right? Like every time you see something that's really good, it pushes the demand that we have.
Yeah.
But the problem is on the flip side, like there's no improvement in computer architecture or chips or software that's getting people to that point.
Right.
So the artists keep getting crushed and more crushed and more crushed and more crushed. There are
Right.
books about like essentially crunch time in game development and film development because tools are lacking and like
Right.
people don't think about how long it takes to make these things, and so they just get stuck and the artist gets crushed by it. And so it just became really interesting just to think about like I love playing games, love watching movies, I love this kind of 3D content that's coming out, but it's limited to like 5 or 6 companies in the world. And just the tools are so expensive, they're hard to learn. It's just crazy. I think this is an industry that needs to get revolutionized. And I think we've at Bolt we found a way to take the graphics part and bring it into simulation, which gives us a great like dual market opportunity
Yeah.
to solve the enterprise side as well as like let's make things look better, great things look even better.
Right. And when we tap this in to healthcare, where they take a voodoo doll like me, a dude in his 50s with a certain ethnicity and genetic predispositions, and these tools then can compare me to the protocols that other voodoo dolls like me went through to get to their optimal health, all of this other stuff, it's going to create even more demand. Like it's just exponential. But when we create that demand, I want them to create the demand, but I need, to your point earlier about the AI tools helping you develop even more efficiency. So that requires uh, cores deployed.
Mhm.
I need systems that are protecting the white hats from the black hats, so they're not interfering with any of this stuff. So that requires a digital defense. All of this requires compute and process, which is another way of saying of power. We don't want to heat the Earth up to this is the only spaceship we got, so we don't want to burn it up. And so this complexity of pursuing the opportunity that comes from the infrastructure without at the same time creating an environment that's not sustainable, like a literal, it's too much power. We've got too many things going on. And I'm really bullish on the potential of this stuff, but we got to live in this world that we're making. And so one of the things that sort of the theme I think I've heard you say throughout this is as we go about pursuing these things, we cannot lose sight of making them efficient. We have a finite amount of resources, intellectual power to think about these things, but also we can't just keep stacking cores up and making things bigger and bigger and bigger just for the sake of making them bigger and bigger and bigger.
Yeah.
They've got to be more and more efficient.
Yeah, I think we're getting to the point where we're going to have to walk a tightrope of like we want to develop more products, we want people to buy more things, all that kind of good. We want people to experience everything as much as
Right.
possible, as much literally as much as possible. But at the current scale that we're hit, like efficiency wise, it's just not going to happen. There's too many people in the world, there's too much stuff,
Right.
and the stuff consumes too much power. So if you think about it, like you're absolutely right, and I think our mission is, to your point, is just to make sure that um, we can solve problems like future problems. It can totally be done really efficiently, like orders of magnitude more efficiently for these key foundational problems that the world's going to have. But it's really important to make sure that power consumption overall just doesn't increase and becomes less of an impact on the world, because I can imagine if you know if you, there are some VCs that like to think that the market for gaming is like 8 billion people. But if you imagine like every 8 billion people buying GPUs, that's a lot of GPUs you're going to have to sell, right?
Yeah.
Every 3 years, every 2 years. And you do use some quick napkin math on like how much power that is. It becomes out of hand really quickly. So I think it's a great market. I think um, uh, computer graphics is becoming culturally really important. Like
Mm.
everyone is really comfortable now with seeing animated pieces. They're comfortable with going and seeing a watch advertisement. That's completely consumer. It's completely computer generated. Like there's
Right.
nothing real about it at all. It's complete rendering, but it looks perfect, right? And you can go buy a Rolex because hey, it looks like what's going to look like, and that's going to become really important. And I think the concern that we have is just essentially power consumption is going to keep increasing. People like
Right.
you are going to have to figure out how to build multi-gigawatt data centers, buildings,
Yeah. What?
which is fun and scary.
But as you look at the embracing of large language models, and that's, well, that's getting a lot of attention. There are so many other applications out there that are really pursuing the benefits of this infrastructure. Do you think the marketplace for you guys is going to double, quadruple? Is it predictable? What's the potential, I guess, in general? And then silicon IP providers like you guys, do you see your role growing even more relevant? And I don't mean that like as a straw man. I'm really curious to hear
Yeah.
what you think about it.
Yeah. So I think your second question is really interesting. It's something that has changed over, I think, the past like 6 years is um, a lot more companies now are looking to make chips
Mm,
than previously. Like if you looked at 7, 8 years ago, Microsoft wasn't making silicon, right? Apple was very new into making silicon.
right.
And now all these companies are becoming really vertically integrated. The cloud providers, and you know this really really well.
Yeah.
Cloud providers love to make their own chips to get better power efficiency, cost
Right.
metrics. I think most importantly, and so I think from an IP provider perspective, we're in a great position because everyone's going to want to make chips. Everyone's going to want some differentiation in their cloud platforms, and that's what we can provide, right? To your point about us being agile and just providing a better product, we can enable that for those guys. Um, uh, in terms of I think like how the market's going to evolve, I'll say that the limitation today for the market growing is the easy availability of the technology that we're building.
Mm,
It's just too expensive to
mm,
to make lots of movies if you're unless you're Pixar or
right.
the really large studios. On the enterprise side, I mean, unless you're going to go build a data center that can emulate a wind tunnel for your $1 billion wind tunnel that you built a few years ago,
Right.
it's not going to be cost effective. Like startups can't do this today.
Right.
And so there's in both consumer graphics and in digital twins, there is a huge gap between what the big guys can do and what everyone else can do kind of in the market. And maybe like you and I can do some stuff on our laptops, but it's not going to be like something that we can really scale.
Hmm.
We can't simulate the complex things with that. And so I think the market's going to grow. It's going to grow very quickly because it's just going to be much less expensive to simulate things versus making them. And so that's going to be the driving factor, is literally just the cost difference, the cost efficiency that you can gain from that. But it's not possible today. So we're really looking forward to releasing our products and to letting people use this, because we think that market is like not measurable today. It's really difficult for an analyst to go in and look and say, okay, this is like this many billions of dollars, because they just can't simulate. They can't do it today.
Right.
But in the future, we think everyone can do it. And we even think that there are content creators that are like just regular people, like teenagers, kids, people like you and me, maybe eventually we'll be sitting here, creating like actual like 5-second animations of things that we think are cool that we thought about in our heads. We just didn't know, didn't have the skills, didn't have the good access to easy tools and technology to make those things. But we think the market's really limited here. It's just the number of people that can access to the technology. If you think of a company like Etsy, right, which is like enabling people to create things on the side,
Right.
create little businesses, like you can imagine what if that was enabled by digital twins, a simulation environment where maybe you're not just like knitting things now, you're going into like making real products. And so I think the market's going to change very significantly. It's not going to be 3 or 4 companies making everything for everyone. It'll be a lot of people making, lots of little things that are optimized for their use case. And I think we'll see just like a much better product market fit for products that come out that are tailored. Like the shoe, I think is a great example, right? It's like, okay, we know how the shoe is going to behave. Dave, I know you need this exact shoe. We simulated this exact shoe on a foot that looks like yours
Right.
on the sidewalk that's right outside this house, but on a computer. And that's like a perfect product market fit there. And you just can't achieve that today because you can't simulate it.
Right. That's what I love about conversations like this, because I want to give you the ability on a small scale or a large scale for you to get involved in something like this, to use your imagination and create freedom for yourself. You win, they win, the customer wins. What a great idea.
Yeah, it's a huge win for everyone, and in the end, it's just there's less waste, right? Because you're
Yeah.
not like trying to make one shoe that can sell to like everyone. Why even
Right.
bother? Well,
Right.
like why go through that effort? And you can think of like there's an end-to-end here where like someone can scan their foot, send it into a service. Service will go like design, simulate, automate, like all this kind of like you can think of a full end-to-end where it's like you can get a perfect fit, no waste because it's for your
Right.
shoe. You have the design forever, by the way. So if it goes off the shelf, like you don't have to go find another shoe. Like
Right.
this is a problem that I have. Like a shoe will stop being sold, and it's like, well, now I have to go like online. I have to go buy a shoe, or I have to go to a store to like try it on. I get a really limited. I can talk forever
Yeah.
about this. Sorry, I'll
We'll do
I'll
it.
stop there. But it's crazy. Like there's so much efficiency that you can gain from just optimizing these little parts of the. I say little parts as if
Yeah.
it's like easy to, but these key but like really important parts
Yeah.
of the end to end for like idea all the way down to a product that like actually works perfectly
Right.
on first fit for that user.
You're right. We could do this all day, but let's pause there, Darwesh. Thank you so much for coming on. Hey, if people want to learn more about you, how do they find you?
Yeah, we have a website, bolt.graphics. You guys can learn more about the problems that we're trying to solve, as well as contact us there. I'm available on LinkedIn.
Okay.
I don't know if we can do like a little thing. I can include like my contact info
Yeah.
after. So,
We'll link,
yeah.
we'll put the links down below for everybody to get to. Thanks for coming on today. I really appreciate it.
No, thanks for having me. I really appreciate it. This is a great conversation. That's always great to be able to talk to people like you that understand the problem and that are in the industry. I love
Right.
it.
And we're curious and we're learning. So thank you again. And hey, look, if you enjoyed the conversation, like us, and if you loved it, subscribe. We'll see you next time, everybody. Have a good one.